Today we talk about zeros of polynomials, and we need to remember that a zero is basically just an x-intercept. So we're going to be finding out where graphs hit the x-axis. But in order to do that, we needed to develop a little bit of understanding about a division. If I take just regular numbers, take 2 divided into 3, that's the same as 3 divided by 2, or 1 1/2, which really is 1 plus a remainder of 1/2. If you think about it. Alright? So, if I were to take and multiply my original number that I was dividing into 3 by my answer, then I end up with 3 coming back. That's the whole concept behind division. And the same thing goes for polynomials. We take a function, divide it by another function, we get an answer, plus some remainder divided by the original divisor. Alright? So, and then there's a remainder left over. Now, taking that one step further is if we want to define that remainder and let f be some polynomial, if you were to take and divide that function by some binomial in the form x minus c, the remainder is actually going to be the value of the function at that c term. So let's go through and do this. Here's a long division of a polynomial. I don't want to do long division, so I'm going to do synthetic division, which we should all remember from last year. So synthetic division states list the coefficients of x in decreasing powers of x. So I have 3. There is no x to the 4th term, so I put a placeholder. -7 for the x cubed term, 1 for the x squared term, 0 for the x term, and -7 for the constant. And I'm going to take and divide by c. Now if this is in x minus c form, then c in this case will just equal 1. So I'm going to put a 1 right here. Synthetic division, remember we bring this first term down, we get a 3, multiply 1 times 3, get 3, and add. Multiply 1 times 3, get 3, and add. Multiply 1 times -4, get -4, and add. Multiply 1 times -3, get -3, and add. Multiply 1 times -3, get -3, and add. And if you remember, this last term is our remainder. That should all have been done last year. Now what I'm saying is that if I were to take and find f of 1, I should get out my remainder of -10. Well, let's go and do that. I take and plug 1 into this function, so that's 3 times 1 to the 5th minus 7 times 1 to the 3rd plus 1 squared minus 7. And I better get -10. So here's 3 minus 7 plus 1 minus 7. I've got -14 and 4 is -10. So be it. So I don't even need to go through this synthetic division to find my remainder. All I need to do is plug in the c value to the function in order to get the remainder. And this is called the remainder theorem. Next, we're going to use that remainder theorem to find all the remainders of these divisions. So again, rather than just take and do long division here, I'm going to take and find the values of c and plug them into the function to get the remainder. So in this case, if this were in x minus c form, then it would have to look like x minus a negative 2. So in this case, c is equal to negative 2. So if I want the remainder, I need to take and find f of negative 2. Well, then that means I've got 5 times negative 2 cubed plus 6 times negative 2 plus 8. When we go through this, we have 5 times negative 8 plus negative 12 plus 8. Leaves me with negative 40 minus 12 plus 8, which is going to give me 44. And that's the remainder of my function. So let's go through it. In this case, we notice this is in x minus c form. So c is equal to 2. I'm going to pop my 2 in. This is a negative 2 to the 4th plus 4 times 2 cubed minus 4 times 2 squared. I end up with negative 16 plus 32 minus 16. And in this case, I get a remainder of 0, which then means if ever I have a remainder of 0 after dividing into a function, that the term x minus 2 is a factor. And if it's a factor of the function, then it's an intercept. Because that means the function is equal to 0 then. So now we're going to talk about finding actual intercepts. And specifically, we're going to look at rational intercepts. In other words, intercepts or zeros that are fractions. Now, let's read through the math mumbo jumbo. So we're going to look at a polynomial. Here's this polynomial in the box. All right, and we have all the coefficients in front are going to be integer values, so no fractions. All right, and if we let this quantity p be factors of a sub o, in other words, this number here, and q be factors of a sub n, in other words, the leading coefficient over here, then we can say that all the possible rational zeros of this function are of the form p over q. So, in other words, let's apply this to a problem. My p-values come from my constant term. So what I need to do is I need to look at all the factors of 6. And if I look at all the factors of 6, I've got the following possible p-values. Plus or minus 1, because 1's a factor of 6. Plus or minus 2. Plus or minus 3. And plus or minus 6. Those are all my factors of 6. If I look at the coefficient in front of the first term, that's my a sub n term once again. Those are going to relate to q. There's only one thing that multiplies to 1, and that's plus or minus 1. So really, if I take all my p over q values, it's just each of these divided by positive or negative 1. So in other words, it's plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. And these are our possible rational roots, or our possible x-intercepts. Now that doesn't mean each one of these is an x-intercept, it's just the ones that are possible. So what we're going to do next is we're actually going to find those x-intercepts. So once again, here's the same function, and we're going to take and we're going to test some of these to see if they're actual zeros of the functions. In other words, are they factors? If they're factors, then they divide evenly in. So let's go ahead and just try 1, because that's an easy multiplication to do. All right, and I'm going to pop that into coefficient of 1, -1, -5, -1, -6. So I'm going to do synthetic division. All right. In theory, what I could do is I could plug each of these numbers in to f of x and see if my remainder is 0 and work out the problem that way. That's another option. But I'm going to do this using synthetic division. So I go 1, multiply, get 1, 0, 0, -5, -5, -6, multiply -6, and I get -12. Since I have a remainder that's not equal to 0, that's not, the 1 is not a root. Or a 0. So now let's check another one. Let's go to -2. Go into the same function. -1, -5, -1, -6. Do that division. Put in a 1. Get out a -2. -3. Multiply, get a 6. Get a 1. Again, -2. -3. Multiply, get a 6. Now notice in this case, I get a 0, which means this is a factor and a 0. So one of my rational zeros is a +2, or I'm sorry, a -2. Just do another one for kicks. Let's guess at, I'm going to go 3. Now, here's what I'm going to do instead of plugging this in to the function that's originally here. If I know -2 is a factor, then when I take and write out my factored function, this is what's left after I divide x minus 2 in. So I'm going to take and divide into this new function, and if 3 goes into that, I know 3 is a factor as well. So I divide, get a +3, 0, 0, 1, 3, 0. What do you know? This is also a factor, or a 0, at -2. Now, notice what I have left here. In this case, we said this was my remainder. What's left is the value of the division. And working backwards, this is a constant term. This is an x to the first term. This is an x to the second term. So if I were to list out the factors of my function in their entirety, what I have is I have the original, which was x to the fourth, minus x cubed, minus 5x squared, minus x, minus 6. And what I've just found out is that this actually factors into, if -2 is a factor, or a 0, I have x plus 2. If 3 was a factor, I have x minus 3. And then what I have left is I have x squared plus 1 is my last factor. Now, think about if I were to solve this problem and say, when does this equal 0? When does it cross the axis? Well, in these two cases, since they're factors, I can set those equal to 0 and solve and get -2 and 3. However, in this last case, I have a quadratic, and if I set that equal to 0, I'll have -1 equals x squared. I know there are no rational factors in x squared plus 1 because it's not a factorable term of my original polynomial. So this tells me, in this case, I'm done. We're going to find all the possible rational zeros of the following function, but we're going to use a calculator this time. So why don't you get that out and get it ready. So what I've done here is I've taken and gone to my y equals, plugged in the function, and the next thing I'm going to do is graph this in the standard window. So I'll hit zoom 6, graph it in the standard window, and I notice here's the function. It's a cubic, so it goes up, down, and back up. And it hits in these spots here. Now I know my possible rational roots for this are going to be in the form of p over q, where p are all the factors of 6 and q are all the factors of 2. So I have plus and minus 1, plus and minus 2, plus and minus 3, plus and minus 6. And that's going to be over plus and minus 1 and plus and minus 2. Now if I take all the p over q values, then I would get plus and minus 1, plus and minus 2, plus and minus 3, plus and minus 6, plus and minus 1/2, and I get that from the 1 divided by the 2. If I go 2 divided by 2, that's 1, so I already have that in my problem. I get plus and minus 3 over 2, and that's taking the 3 and dividing it by the 2. And then if I go 6 divided by 2, I have 3, which is already in my p over q values. So in this case, I would actually, if I were doing this the long way, have to check 12 actual pieces to see if those were possible zeros of the function. But like I said, we're going to use a calculator to help us out. So what I'm going to do here is say, all right, let's graph that. We did. And I can see clearly that there are 3 intercepts. I want to know if these intercepts are actual rational roots. In other words, do they come from this list? Now there's a lot of ways to do this. What I'm going to choose to do is, rather than set it equal to 0 and find the intercepts, I'm going to guess using my table. So I'm going to go second table set, and I'm going to make sure my table set is set on my independent to ask, and then I'm going to go over to my table. So second graph gets me to my table. Now it looked like on that graph -3 was a possible root, so I'm going to plug that in, and sure enough it was. Now here's the deal. I know -3 is going to work in synthetic division, but I need to know what's left after I divide by -3. So what I'm going to do is I'm going to prove, first of all, that -3 was a root, and pop that in, do a little synthetic division. So I have 2, 1, -13, and 6. I get 2, -6, -5, 15, 2, -6, and 0. Now notice, this is 0, or a root, at -3. So if I were to factor this, I would end up with x plus 3 times 2x squared minus 5x plus 2. Because my remaining factor has a 2 in the end of it, I can pretty much rule out that 6 is even going to be a possibility. I can go back to that graph and check a couple more terms if I like. And I think I will, just for kicks. Alright, so let's go back to the graph, take a look, and it appears that maybe 2 is an actual value here. So I'm going to plug in 2 to that table. And I notice, hey, 2 works as well. So I'll go in and I'll say, okay, well, now if I take and divide into 2x squared minus 5x plus 2, and I divide 2 into that, and I've got 2, negative 5, and 2. This should also equal 0. Bring my 2 down, get a 4, negative 1, negative 2, 0. So again, I have a 0 at 2. So now if I look at my factoring, notice what I have left. I have x plus 3. I have x minus 2. And then here is what the other factor would be. This is, remember, my constant term and my x term. So that's 2x minus 1. And I would have got the same thing by factoring this polynomial up here. Notice, I say, okay, what multiplies to 2? That's 2 and 1. And then what multiplies again to 2 but gets me negative 5? I got a negative and a negative. There's a 2 here and a 1 here. And there we have it. So I have zeros of negative 3, 2, and 1/2. Because that's when the function would equal to 0. So that's a nice way to use your calculator to help you go through and find all the zeros. Let's do it again, except this time we're going to find out that we don't just have rational zeros. We're going to have other zeros that are not rational, in other words, not functions. So again, we're going to go to our calculator. And once again, I've plugged in the function to the calculator and I'm going to graph it. Let's go back to the function and determine our possible rational roots first. So we have our p-values right here and our q-values right here. So possible p-values are plus and minus 1 and plus and minus 3. And the q-values are plus and minus 1. So really in this case, my p over q's are just plus and minus 1 and plus and minus 3. There wouldn't be actually that many to test in this case. I could probably do this without the aid of a calculator, but we're just going to do that to make things a little bit faster. So I take a look at the graph of this function, and if I have to pick between plus and minus 1 and plus and minus 3, I look at the picture and say, well, 1's pretty much out, negative 1's out, nothing over at 3, so I'm going to go with negative 3 as my possible root. So I'm going to go back to that table. I'm going to see if negative 3 works. Plug it in. Sure enough, it does. Now I'm going to prove this with synthetic division. So I'll go over here and I'll say if I plug negative 3 into my function, I'm going to get out a remainder of 0. So let's make sure I do the math right. Here's negative 3, 4, negative 12, negative 1, positive 3, and 0. So notice what I have. I have a remainder of 0, so this is a factor. Negative 3, which means when I factor the original polynomial out, I get x plus 3 times whatever I have over here. Once again, this is my constant term, my x term, and my x squared term. So I have x squared plus 4x minus 1, and that's equal to f of x. Now if I wanted to know where do these hit the axis, I need to know where y is equal to 0. I know y is equal to 0 at negative 3 because we already found that out. We said these aren't going to be rational. They're going to be irrational. In other words, in order to find these roots, we might have to go to the quadratic formula. Negative b plus or minus square root of b squared minus 4ac over 2a. And we could find those pretty easily just by plugging these numbers in. So I got negative 4 plus or minus square root 4 squared minus 4 times 1 times negative 1 all over 2. And that's going to end up getting me roughly negative 4 plus or minus 16 plus 4 is 20 over 2. This is going to simplify to negative 4 plus or minus 2 root 5 over 2, which again reduces to negative 2 plus or minus root 5. So I actually have 3 roots, one of which is rational, and that being at negative 3. And then I have negative 2 plus or minus root 5 as my other 2 roots. However, this is not rational, and the only way you're going to get that is by showing the factored form, having it reduced to a quadratic, and then using the quadratic formula to take and find that irrational root. That's all we've got. We'll see you tomorrow. Make sure you do your summary.